Good afternoon, good evening, or good morning, depending on where you are in the world, and welcome to the second installment of today's webinar, which is on IEC 61511 and failure rates. And judging by the response we've had in terms of registration for this particular webinar, this is obviously a subject of significant importance to people. So I'm glad we were able to do this. Again, looking at the registrants, there are people here that are coming to us for the first time. So bear with me, those that are very familiar with our exida webinars, and I will just explain a little bit about exida itself and where we've come from and what we do, and a little bit about myself before we get into the webinar. So exida has been around for 20 years. This was supposed to be our 20th anniversary year, and of course with COVID we weren't able to have the celebration that we wanted. So instead of having a 20-year, we'll probably have a 21st year next year at some point. But exida was originally founded back in 2000 by two original founders, and they set the company up primarily to help manufacturers understand and get to grips with what was then the new IEC 61508 standard that had just been released. There was a draft that was released in '98, but the actual first release was 2000. And they started exida to help companies get to grips with the requirements. Since then, starting with product and product certification, we have grown exponentially. We now not only do product certification for functional safety, we also do product certification for cybersecurity to the new IEC 62443 standard. And we also do personnel certification with our CFSE, CFSP for the safety, and our CACE, CACS for the cybersecurity. CFSE is Certified Functional Safety Expert. CFSP is a Certified Functional Safety Professional. CACS is a Controls Automation Cybersecurity Expert and a Controls Automation Cybersecurity Specialist. Those are certification qualifications. And the difference between a certification and a certificate is that if you take one of our courses, for example, there will be a 1-hour exam at the end of the course based upon just the course material. If you pass that, you get a certificate. Whereas with certification, it's more than just the course knowledge, it's detailed knowledge of the standard as well as practical application, and it also has ongoing requirements. Every 3 years, you have to show you're maintaining your level of expertise, rather similar to a PE type certification. In addition to that, we now offer the full lifecycle services for cybersecurity, functional safety, and alarm management. And all three are very closely regarded when it comes to overall process safety. They all three have essentially the same three lifecycle phases. There's some form of analysis phase, there's a design and implementation, and of course there's an operation and maintenance phase. So we now provide full lifecycle services for those three particular disciplines. To support that, we have a comprehensive set of tools, the Excellentia tool, to allow us to provide support for the life cycles. We are also a global company. So from our humble beginnings, we are now well established across the globe. We are in the process of finalizing a new legal entity. I won't spoil the party by saying where that is. There will be an official announcement at the right time to let everybody know. But that's another sign of that we are investing and growing across the globe. And of course, the beauty about the three main disciplines from the services point of view, the cybersecurity, alarm management, and functional safety, is they're almost, well, we regard them as being industry agnostic. In other words, they can apply across any industry that has these requirements. So for example, not just the process industries, but food and beverage, automotive, robotics, machine safety, as well as steel, energy, any of those, pharmaceuticals, they all apply. Just a bit about me. I've been in industry for over 40 years now. I started life off as a design engineer doing hardware and software development for a controls company, and then I moved to a safety company, and we started doing emergency shutdown, fire and gas, and addressable fire detection systems. From there, I moved into more of a sales and executive role, and then I joined an automation company, and then finally coming back into safety when I came back to Exida in 2012. And my role in Exida, depending on who I'm talking to, is I'm responsible for our overall services, for the services I talked about for cybersecurity, functional safety, and alarm management. I'm also one of the primary instructors for the functional safety and the alarm and the cybersecurity courses that we offer, and I have a global business development responsibility as well. How do we measure success? Well, from the original two founders, we've moved towards more of employee ownership, and that was a deliberate move by the founders because they will eventually retire, but they want the company to continue and be successful and grow. And so this is what's happened over the interim. We've also now got well over 100 global experts around the world. We've done over 1,000 certification assessment projects, and we've modeled well over 500,000 SIFs with our Excelencia tool. In certification that I've mentioned to you, not just the product, but also the people, which is very important, especially now that the 2016 edition of 1511 puts more emphasis on the need for personnel competency. If we look at the market position of Exida, we're actually the leader now based on market research that was done independently. And this came as a surprise to us as well, which is a nice surprise. And the other thing that we do also is a lot of material is available through the website. Now, of course, there are these webinars that some of you are familiar with and do attend. These webinars are recorded. They're recorded as YouTube videos. They're available through the website. If you go to the exida.com website, look under resources. There's a tab called resources. If you look under that, you'll find that the webinars are listed. So the upcoming webinars are listed, but also you can go and look at the archived ones, which is the YouTube videos. So you can search under certification. You can search under functional safety, you can search under alarm management or cybersecurity. So they're there. The other thing that we provide is our SAEL, the Safe Automation Equipment List. If you look at the website homepage in the top right-hand corner, you'll see the SAEL. That basically gives you a list of certified devices. So if you're a SIF designer and you're looking for a specific certified device, then you can go in there and see if there's one for a specific manufacturer that you had in mind, or if not, there might be another manufacturer's device that you can use. And you can access the certificate from the website, and if we're allowed to publish it, you can also access the assessment report, which says how we came up with the failure rate numbers. We also have a number of white papers that we've written on various subjects, which are available through the website. And you can also purchase books. We've written a lot of books. And I have just finished a book, which is in the printers at the moment, which is Functional Safety for Managers, what managers need to know. You can also purchase the SERH, which is the Safe Equipment Reliability Handbook. In other words, all the failure rates. These failure rates are automatically built into the Excelencia tool, which makes Excelencia a very useful tool when it comes to doing SIF design and SIF SIL verification. I mentioned Excelencia already. We have various modules of Excelencia, which are either standalone or you can buy the complete suite. And there's the PHA tool. So if you need to do a hazard and risk assessment, the FACS tool can handle that. We can also import from PHA Works or PHA Pro or through a CSV file. And once it's in FACS, then it's available to all the other Excelencia modules. From the PHA tool, we can export LOPA candidates into the LOPA tool. Once we've done LOPA, we can do the selection for the SIL and then create the initial process SRS from which we can then do the conceptual design, the SIL verification, and the detailed SRS can be printed out from the Silver tool. The SIL alarm tool allows us to create a master alarm database. So if we've got any alarms that we are going to use as protection layers that come out of the PHA and LOPA, they can be built into the SIL alarm tool to start creating the master alarm database. If you're looking at doing rationalization, right now the SIL alarm tool can directly import and export to and from the Delta V or from the Rockwell plant PAX. Other platforms, we can use the CSV format for doing that. So this is quite a popular tool for helping to create master alarm database and do SIL to do alarm rationalization. The SILstat tool is the tool that you can use for data gathering. Now under 1511, under the 2016 edition, we have to do what they call a periodic assessment of performance of the SIS and its SIFs. So that means that we need to be able to gather performance data. So the SILstat tool can take the design that's done in the Silver tool, including all the proof tests, bring it into the SILstat tool and use SILstat to be able to run the proof tests in a tablet in the field, record results, record incidents, record near misses, look at what failed and what didn't, what passed. So all of that data is available for analysis. And right now we have the ability to export from SILstat into something like SAP or any other asset management system. We are investing heavily right now in the development of SILstat to encompass other features. So like I say, these can be purchased as individual modules, SILstat, SIL Alarm, LOPA, and PHA, or you can purchase the entire suite. And we can do that because of the way we structured the database. So we can, as I said, once we get the data into any one of these tools, it's available to all these other tools that are there. And if you have the complete suite, you can cover the life cycle. We've also developed a cyber PHA tool, which can be purchased. So if you want to do risk assessments from a cyber perspective, you can purchase the CyberFacts. And we have the cyber equivalent of the LOPA tool called the SL tool that can also be, so you can determine what security levels you need from doing your risk assessment. All right, so having done that introduction, let's get to the meat of all of this. And we're looking at IEC61511 and failure rates and what this means for any SIF equipment justification and for end users. So if we consider 1511 requires us to justify equipment selection. Now, some of you may have or may not have seen the webinar I did about a month or so ago on the prior use justification under 1511, because 1511 requires us to have two methods of justification. The first is the use of IEC 61508 certified equipment. So here you can use certified equipment as long as it comes from an accredited certification body or some other means that is justifiable, and we'll get onto that in a minute. Or we do prior use justification. The primary purpose of prior use is to make sure that there are no potential systematic failures that could occur with the device. And there's a whole slew of requirements for prior use that I covered in the previous webinar. When it comes to doing the SIL verification of the SIF, we have to make sure that we have failure rates for both the safe and dangerous random failures. So in other words, random failures are used in our PFD average calculations for low demand or PFH for high or continuous demand. So we have to make sure that we have the correct failure rates for that, as well as making sure that the SIF from an architectural point of view meets the SIL requirement and we meet the systematic capability. So when you use certified devices, if they are certified to IEC 61511, then they will meet a certain systematic capability level. So if you're using certified devices, then that's a good way of doing the justification for the selection. Now, we know that in a SIS application, we expect the SIS to be able to respond to a demand. And the thing about safety instrumented systems and safety instrumented functions in the process industry, the majority of the time, we are looking at low demand applications for the SIFs, which means that they're going to be sitting there static, not doing anything for very long periods of time until a demand occurs. Now, if a demand occurs, we expect the SIS and its SIFs to respond automatically to bring the process to a safe state. If they fail to do that, then the consequences can be potentially catastrophic. So from a safety engineering point of view, we have to determine the probability of a SIF failing on demand. It's the probabilistic calculations that we need to do. And these probabilistic calculations are performed using random hardware failures for our PFD average and our PFH. For SIL rated devices, these will have stated values of safe and dangerous failures. And if they are intelligent and have some diagnostics, there will also be diagnostic failures stated. This information is usually in the safety manual, but also you'll find it from the exida point of view. If you go to an exida certificate, on the second page you will find the failure rates. So these are available, so you know what they are. If you're using Excellentia, that information is already in the tool. So if you're using a specific manufacturer's device, then that device's failure rates are automatically in the tool, and when you select the device, the tool automatically uploads those failure rates. If you're doing it the hard way using Excel, then you have to make sure that you get those failure rates to be able to plug into your formulas. So we all know, or most of us know, that failure rates are represented by the Greek symbol lambda, lowercase lambda. And failure rate basically is the number of failures per unit operating hours. Simple enough. And of course, we know that failure rate will vary with time. And we approximate with a constant number based upon an average over a period of time. So this we will get to in a couple of slides when I talk about this a little more detail. But we know that things will eventually fail. They wear out, because what happens is over time, the normal stresses and strains placed on the equipment during normal operation will eventually overcome the strength of the equipment. That's wear out, basically what happens. And from a failure rate point of view, we can divide these into dangerous failures, safe failures, enunciated failures, and no effect failures. Now, when it comes to trying to figure out the probability of failure on demand or failing dangerous, this is where we focus on the dangerous failure rates. But we also need to know the safe failures, because we will have some spurious trip target to meet. Spurious trip, these are trips that occur unwanted, unexpected. They don't cause a problem other than the fact that they trip. And of course, we know that in some applications that if we have to restart after a trip, that can, number one, be costly, but number two, can also involve quite high risk. So clearly we don't want to be having what we call spurious trips, unwanted trips. The enunciated failure rates will be for, if the diagnostics fails. If the diagnostics fails, then we potentially could have dangerous failures that are not detected because the diagnostics are not running. And no effect failures, an example of which would be if you have an instrument with an LCD display. If the instrument is operating normally, the control room operator can see the device, can read the current values clearly, but when you look at the LCD is blank because the LCD's failed. That's an example of a no effect fault, because even though the LCD has failed, and okay, it's inconvenient because we can't see the reading in the field, the device is still functioning perfectly from a safety point of view, and the operators can see the values. So if we look at our pie for the total failure rate, you can see that we can split it into the dangerous components, the safe, enunciated, and no effect. So dangerous, as I've said, this is where the SIF will fail to perform its function when a demand occurs if we have a dangerous failure that we haven't found. The safe failures, it'll just trip when we don't want it to trip, of course, and enunciated, as I said, the diagnostics are failing to run, so we can't find potential equipment problems. And no effect has absolutely no effect on safety. So how do we get realistic failure rates? Well, coming back to what I said earlier about taking the average over a period of time. Most manufacturers will know this. This is called the bathtub curve, and this is typically how any equipment or device normally will behave over a specific amount of time. So you can start off with a whole bunch of equipment working, and very quickly you'll see that there's some high numbers of failures. It sort of stops, and then it starts to flatten out a bit until after a certain period of time it ramps back up again. So at this point, this is known as infant mortality, and what most manufacturers will do is they will do some form of stress testing to be able to wheedle out weaker components before they get into circulation, because they don't want warranty returns, of course. And then what happens here at the back end is what I was talking about earlier with the wear out, where the normal stresses and strains start to overcome the strength of the device or equipment. This bit in the middle, as you can see, if we take the average, slightly pessimistic, but you can see we can, by doing this, we can approximate to a constant failure rate during this period of time. And this is between this point and this point is known as the useful life. And all our probabilistic calculations are predicated on this concept of constant failure during useful life. So once you get outside of useful life into wear out, then all bets are off because it's no longer constant failure. So again, if the time of failure is recorded, or the number of failures for a small time interval is recorded, and we use 1 hour as the smallest time period, then you can calculate a failure rate. So we usually express failure rates for a given hour and time. And you can use this formula of lambda equals delta NF, where the delta NF is the number of number of failed units during a time period divided by the number of successful units left times the time period. So this is the approach that's taken. And where do we get our realistic failure data? Well, ultimately, failure rate data has to come from one source, which is quality field failure data. The device is operating in a similar application. The challenge there is that a lot of the end user systems in place are either inconsistent or they're not to a certain level where you can depend upon the accuracy of the information that's recorded, which is a shame, because when I teach the class, this is one of the things I say to all the end users is your own plant is your best source of data. So where do they come from then? Well, from that, we should be able to estimate our failure rates based upon this failure data. So obviously, if the failure rate data isn't very accurate and isn't reliable, then our estimation of our failure rate itself is going to be questionable. The other way is to do a failure rate prediction. using prediction techniques such as FMETA as one approach, or you can do it as a mix of based on design strength analysis and test results. So where do we get it from? Well, we can get it from manufacturers, because manufacturers have field return studies. Now, the thing you have to be careful about with manufacturer field return studies, I mentioned this earlier about most manufacturers will want to wheedle out the weaker units before they go into population, because they don't want warranty returns. So the other thing is, what happens when the equipment goes outside of warranty, and also what type of equipment? Most end users I've spoken to, if they have a failure of a sensor, they won't send that back. They'll throw it away and put another one in, because it costs more to send it back than it does to just put in a replacement. So one of the questions clearly is, can manufacturers truly say they know what units have failed? They only can see what's come back from the field. The second thing is, what happens if it comes back from the field, goes through the usual manufacturing testing, and no fault is found? What happens then? Is it recorded as a failure or not? And when I used to work as head of development for ICS back in the 80s, I would get called over by our customer care department saying, look, we've had this module come back from the field, we put it through the test, we can't find anything wrong with it, can you put it through your design test? Now, our design testing was a little more rigorous, and oftentimes I couldn't find a problem with it. So I would go back and say, well, we don't know, it's no fault found, it's fine. So that certainly wouldn't be classified as a failure, and it would go back. The other thing is time. A lot of manufacturers will assume that as soon as it's left the factory, it's in service, which of course we know that's not necessarily going to be the case, because they could be going into storage as spares. They could be waiting for commissioning activity to be available at site, which could be 12 to 18 months after shipment. Who knows? So that's another thing. And one of the problems is with manufacturer field return studies is some agencies are not taking a view. They're simply taking the data that the manufacturer has given based upon, we've been manufacturing these devices from this date, we've supplied this many, we've had this many come back, and they base it on that time frame as being the operational hours, and then they come up with very, very optimistic failure rate data, which some agencies don't. They simply take that, they number crunch, and they come up with a failure rate. So it's very dubious. Industry databases, that's another good source of information, and there's quite a lot of data out there now. IREDA, for example, which is the Offshore Reliability Equipment Database, which is operated by DMV, and the data is reviewed by Syntef, is based on information from North Sea oil platforms. There's also, Dow has a lot of data. There's a pipeline company that publishes data. And of course now the CCPS, the Center for Chemical Process Safety, has the PERD, which is the Process Equipment Reliability Database, where they are now developing software and taxonomies to be able to gather field failure data. The other final one is end user field failure data studies themselves. So again, this really depends upon how well and accurate that data is being gathered by the end users and how reliable it is. So there's things you have to be careful with when you're looking at this data. Now, when it comes to our SIF SIL verification, we know that in order to meet, for a SIF design to meet its target SIL, there are 3 design requirements that have to be met. First and foremost is the PFD average, or PFH, which includes the random failures. So this is where the failure data is so important, and the accuracy of the failure data. If we're using highly optimistic failure rate data in our PFD average and our PFH calculations for random failures, we could end up with grossly optimistic results. The second thing is the architectural constraints. And the third, of course, is the systematic capability. So all three have to be met. And of course, the SIL that's determined is from the lowest integrity level achieved. So this is the crux of this. So 1511 now includes this clause 11.9.3, where it says that the reliability data used when quantifying the effect of random failures shall be, so it's a shall, it's not a should, it's a shall, so this is a requirement, credible, traceable, documented, and justified, and shall be based on field feedback from similar devices used in a similar operating environment. Now, why was this language put in there? The language was put in there to try and counteract some of this. So if you see here, this is a sample of solenoid valves with failure rates. And you can see here, this is the IEC derived failure rate for a solenoid valve. This pipeline company field data, the exida average of these types of solenoids, which is slightly more pessimistic, which is what we'd expect because it's predictive, and then Dow. And you can see that these are ranging from around about 180 or 190 fits up to about 1,000 fits. But what about these down here? This is saying that there's half a fit. So basically what it's saying is there's a half a fit of dangerous failures that would occur for this particular solenoid valve. So the language really enforces what reliabilities understand in terms of failure rates. And these are actually, unfortunately, published certificates. So these comparison studies shown that orders of magnitude can be different in the results. So here we're talking about 200 fits. Maybe the average is around 250. And this is talking about half a fit. So how can it be that far off for the same type of device? Well, this is where this question comes in. Does it meet the credible, traceable, documented, and justifiable? Even this one at 5 fits. So let's talk about fits, failure rates and fits. I mentioned that failure rates normally expressed in terms of failures per hour, but the fit is an abbreviation that we can use just to help simplify things. And depending upon, there are two definitions that we've seen for fits. One is failures in time, the other one is failure units. So it's an abbreviated form whereby a fit is basically a billion hours, or 10 to the 9 hours. And of course, it's 10 to the minus 9 per hour. So for example, if we said a failure rate existed of 5 times 10 to the minus 7 per hour, we would say this is 500 fits. Okay, why is this important? Well, understanding what that means is very important. And this is where I talk about the smell test when I teach the class. So typically those numbers that you saw are normally seen for final elements. They're in the solenoids or valves or actuators. So what we want to check is whether some form of electromechanical or mechanical product failure rate passes this smell test, as I call it. So what you can do is you can take, if you want to put it into a more understandable way of looking at it, you can say, all right, let's convert it to years. So the number of years would of course be 10 to the 9 divided by what's being shown as the number of fits times the number of hours in a year. So if the number should be much less than 1,000, that's being very generous. So let's take an example. We had the 5 fits. So what is 5 fits? Well, if you do the math, it's saying that I'm going to get a dangerous failure once every 22,000 years, roughly. Now, any process engineer or any safety engineer, if you said that, they'd laugh at you. and say that's just not going to happen. But that's what that's saying, and that's on a certificate. And this one, half of it, well, you know, that's saying 200,000 years. So why are we getting this difference? Well, again, it depends upon how the assessment was done. One approach we've seen on certain certificates is using B10 data. So what is B10? Well, basically, B10 is really used for looking for premature wear out. So if you've got a dynamic device or dynamic application and you're worrying about wear out, the B10 is the way to go, because what it says is you have to take at least 20 devices or more, you cycle them at a given rate per hour, and then you record until 10% of the population fail. And at that 10% point, you calculate a failure rate. Great. Now that's fine for dynamic operations, because what we're worrying about is premature failure rate, and all other failure modes are ignored. However, when it comes to the process industry, and in particular low demand applications, which is predominantly what we have, we're not worrying about premature wear out because it's a static operation. The thing is sitting there doing nothing. So what we're worrying about now with our final elements is it going to stick? Is there stiction? Is there cold welding? Will there be any binding? Those and several other types of failure modes are what we're concerned about. B10 data isn't applicable in that case for application in a low demand SIF. And yet we've seen devices with certificates that are based on B10 that are being used for low demand. So this is why it's important to know what you're looking at, because these are not credible, traceable, documented, and justifiable when we're looking at low demand. So one of the things we did at the request of end users was to create this website, www.silsafedata.com. And you'll see here that we have different types of final elements. We've got actuators, valves, and solenoids. And you'll see for each of these, there's a range of failures. So the low end and then the high end. So for example, if we look at a solenoid valve that's a poppet three-way, we can see, well, low is 60 fits, high is 400. Solenoid valve that's a spool type now is 450 fits to 1200 fits. So if we look at it here, this would be the limit for the poppet 3.2, and this would be the limit for the spool solenoid valve in low demand, not here. And this is the problem. So the good news is that end users are becoming more aware of this now, and in fact they're rejecting some of these manufacturers that are using, they're going to these agencies that are willing to help them publish these low failure rates as a means of specsmanship to help increase sales. Well, I'm glad to say that the end users are wising up to that, and as I said, maybe that's the reason for the language that was put into 1511 to say, again, credible, traceable, documented, justifiable. So let's just summarize. SIS designers have to justify the equipment that's selected for use in the SIFs per 1511. And as I've said, there's two methods of doing that. There's use of certified equipment to 1508. And here again, even if it's a certificate for a device, you need to be able to look at those failure rates and see, okay, do they match up to the credible, traceable, documented, and justifiable? Or you do the prior use justification. Those are the only two methods. Because I like the equipment, it doesn't count. Product failure rates that are used in these SIF SIL calculations for our PFD average or our PFH must meet this credible, traceable, documented, and justifiable requirement. And if it doesn't, then it's not going to be compliant. Understanding what the fit means or fits mean on a certificate or in a safety manual is essential. And here again, we've seen this oftentimes end users don't have the safety manuals because the engineering company didn't supply it. Well, as an end user, you are entitled to have that safety manual. And so the engineering company needs to supply that because the safety manual has certain information that's very relevant for your ongoing maintenance and health of your SIF and SIS. You can use the smell test to do a quick check to see if it's an order of magnitude or more higher than 1,000 years. And as I said, 1,000 years is being very, very generous because it should be much less than that. So if you're looking at 2,000 years or 10,000 years, it doesn't pass the smell test. So that's an important thing. Sources, AREDA, DAO, PERD, and now you can use SIL Safe to just compare. So if you've got a number that you think, this looks a little too good to be true, go and compare it and see if it lines up. If it doesn't, as I said, if it's an order of magnitude more outside, then it doesn't pass the smell test. I mentioned this already, that end users are becoming more aware of the need for credible failure rates. Because again, if we say that the SIF has a much, much better PFD average than it actually has, then we could be fooling ourselves into thinking we've got more risk reduction than we have. The other thing we've come across, and it doesn't happen that often, but it still can happen, and we had it with a client, is that we did a SIL verification for a client based upon certain valve from a certain manufacturer, and everything passed, and everything was fine. And then 3 months or more later, they came back and said, you know that SIL verification you did for us? I said, yes. They said, well, what happens if we don't use the same valves? And I said, well, it all depends. If they're the same SIL rating, then it should be okay, but we'd still need to do a verification from the SIF point of view. Then he said, after a little while, he said, okay, so what if they're not certified? And I said, well, then all bets are off because we have to do a prior use justification. And I said, so what happened? And he said, well, somebody in purchasing was approached by a vendor who said they had a device that was just as good, lower failure rates, in fact, and was cheaper, but it wasn't certified. And so purchasing went ahead and bought those without confirming this with engineering. So if you're not careful, purchasing can land you in Sturm, which is exactly what happened with this particular client. So this is the point. The failure rates now that we use in calculations have to meet that credible, traceable, documented, and justifiable. And if it can't, then you're not going to be compliant. Okay, I noticed that there's some questions being popped up. So let me take a look and see what questions we have here. So somebody says, will I be able to view this seminar at a later stage because they keep losing audio? Yes, you can, or these are recorded and they will be available through the website. I'm sorry about the audio. I know sometimes people have issues with internet connection. Do you have an example of a practical approach to get around the chicken and egg situation when using components in novel applications without the possibility of a lot of field data? Well, what you can do here is, again, if you have a tool like Excellencia, then you can use generic. So generic devices have slightly more pessimistic failure rates. So you can at least try your SIF design out using that and see if the PFD average or the PFH meets the target risk requirement in SIL level. What else is it? We used to derate manufacturer's data and up the test interval until we had a reasonable amount of data. Depending on process, not all failures are random. That's true. The process has a big effect when you refer to the IRIDA database. Isn't it the PDS data handbook, also from Syntef? It could well be. I know IRIDA has their own set of books. Just going back to, depending on the process, not all failures are random. The process has a big effect. Again, when I did, I've done a webinar on this, and when I teach the class, what I suggest to people is that if you are too quick to dismiss failures as being systematic, then you could end up with, again, low failure rates for random failures. The rule of thumb is to treat all failures as random until proven otherwise. And for example, let's say we had a SIF with a sensor from manufacturer A, and that fails. So, okay, it fails, we record it as a random failure. And then 3 months later, the same manufacturer's type of device, but in a different SIF, also fails. Now, again, we would record that as random, but then we'd say, all right, we've had 2 failures from the same manufacturer for the same type of device within 3 months. Let's look at that, because there may be an underlying systematic issue. But the thing is, we haven't thrown away those failures, and we're keeping them. So you need to be wary of that. Question above, we work in R&D environment. In your professional opinion, do you consider, oh, sorry, we work in environment, so I'm not sure. Okay, if you work in the R&D environments, then again, what you need is credible failure rate data. Now, if you're not using Excellencia and you're doing it the old-fashioned way, then you have to make sure you have a good source of failure rate data. Now, the old 217F is not a good source anymore, and also some of the older information that was available from telecoms is also not applicable. Again, the key wording in that statement in 1511, similar operating environment, similar type of mode. So you've got to make sure that you're comparing apples to apples and not apples to oranges. So from an R&D point of view, you have to make sure you're using the right data. In your professional opinion, do you consider a TUV certificate with PFD numbers credible, justifiable? Well, and again, that's a leading statement. It depends on the type of device. If the data that is shown on the certificate, it doesn't matter who's issued the certificate, if it doesn't stack up to the credible, traceable, documented, and justifiable, then you should not be using it. That's the whole point. The whole point is that we've seen certificates from different sources, so-called certification bodies that don't stack up. Now, one of the things you can look for, if you look at the certificate, usually on the certificate on the front page, there should be what we call an accreditation body logo, an AB logo, which basically says that we are accredited to do this work by this accreditation body. Now, for example, in North America, it's ANSI. So when you look at an exida certificate on the bottom right, bottom left-hand corner, you'll see a blue and white ANSI logo. That means that we are accredited by ANSI to do this work. And that means we have to be audited and we have to follow the requirements for doing 1508 certification. If you do not see an accreditation body logo on a certificate, then the question should be, well, who has accredited you to do this work, to say that you're competent to do this work and to acknowledge that you're following the correct standards to do this work. So I always tell people, if you don't see an accreditation body logo, that should be a bit of a red flag and go ask questions. The other thing is, if you think the failure rate data is low, then you can ask for the assessment report. the assessment report will tell you how they came up with those numbers. If they won't share the assessment report with you, then again, that's another potential red flag. So let's see what else are there. Can we estimate the SIL of any product without products having an automatic diagnostic system? Again, I'm not sure where you're going with that. If you're using, again, if it's a type B device that has intelligence and has diagnostics, then that's covered by the product certification. So again, the product certification will be looking at the diagnostics coverage to help determine the SIL of the product. If you're looking at it from a prior use justification, well, it's a different ballgame. High probability of dangerous failure on demand. Where does this demand come into the calculation of a PFD average? In SIL verification, I think this demand or frequency number is a target number determination. Well, the demand is the demand on the SIF. And again, when you go through identifying from your PHA what your worst case consequence hazards are, you've got a ranking, or there's normally a ranking. And so therefore you would probably do a layer of protection analysis on your critical risk and high likelihood scenarios. When you do that, what you look at is what are the non-SIS layers of protection in place, and then you compare that to the target requirement. So normally, if we're looking at doing a LOPA, let's say we have a BPCS, we have some sort of relief, and we have an independent alarm system. We could say, all right, we'll take a 0.1 credit for each of those. So that gives us an overall of a reduction of 10 times 10 times 10, gives a reduction of 1,000. And let's say our target is 100,000. So we need to reduce our likelihood of fatality according to our ALARP, and this is all done in another webinar that you can see. Then we would be short of 100. And so that would say we would need at least a SIL 2 to be able to pick up that. So the initiating event frequency on the SIF is what comes out of LOPA, because a lot of people get confused with the incident frequency is not going to be the same as the demand frequency that the SIF sees, because if the non-SIF layers of protection are doing their job, the SIF in theory should never see a demand. So that's where the demand comes from. And there's a book, the CCPS produced a book, I think in 2015, with initiating event frequencies, because that's usually the challenge, is how often do we think that there is going to be an initiating event occurring? And so that frequency you would have to feed in to see how often is that going to cause a demand on the SIF. As I understand in one of this webinar slides, per IEC 61511, failure rate data should come from the field. Ideally, yes. Certificate data is not based, yeah. And as I said, FMEDA is predictive. So FMEDA is looking at the design analysis based on from the components up to the overall device or product. And as you saw from the comparison slide, we expect FMEDA to be slightly more pessimistic than actual real data because it's predictive. And it's still within the same ballpark. So it is a valid method, as I said. Does exida plan to do a webinar on alarm management or showcase? Well, we have lots of webinars on alarm management. Please go and have a look at the archived webinars. If you, as I said to you earlier, if you go to the exida.com webpage, you go to the resources tab and click on webinars, you can then go to the archived webinars and look under alarm management, and you'll see that there's a whole host of alarm management webinars. I believe there is another alarm management webinar being planned for either later in September or October. But watch this space. You should, if you're not registered to get our newsletter, please send a note in and we'll put you on the list, because in the newsletter we usually let you know of what upcoming webinars there are and when these are going to occur. Okay, well, I mean, these are all good questions and I thank you. Oh, there's a couple more I see here. Since you gave an example of LOPA and RRF that determines SIF level, should SIF level be dictated by LOPA or 61511 risk graph? Well, again, the layer of protection, the whole point with risk graph and risk matrix is one method to do it. It's qualitative. Whereas you can use LOPA in a quantitative. The difference is with a risk graph or a risk matrix, it'll say you need a SIL 1 or it'll say you need a SIL 2. It doesn't say you need a SIL 2 with a risk reduction factor of better than 250, or you need a SIL 2 with better than 500, or a SIL 1 with better than 50. All it'll do is get you into the ballpark, but you don't know where in that SIL band you are. That's where the qualitative versus the quantitative is different. Quantitative uses frequency-based methods for establishing a valid risk reduction factor. And remember, risk reduction factor is only in conjunction with the PFD average, because the relationship is that the risk reduction factor is equal to 1 over the PFD average and vice versa. So if you know one, you can figure out the other and you can relate that to the SIL. So remember, the risk graph and the risk matrix are basically qualitative methods based upon, and again, these risk matrix and risk graph have to be calibrated against the tolerable risk. So if you don't have a tolerable risk defined, then it's, your risk matrix could be way off. And it usually needs to comply with ALARP as low as reasonably practicable. So again, if you want to know more about that, we have our FSC 100 training course, which we run either as a live streaming right now because of COVID, or you can do it as a self-paced online. I do recommend that course. It's quite comprehensive and it'll give you a lot more insight. All right, if that's all the questions, then I thank you all for your attendance and your questions. And I bid you a good rest of the day wherever you are. And take care. Hope to see you on another webinar soon. Thanks, everyone. Oh, by the way, if you do have further questions, you can contact me here and let me know. I'm happy to answer them. So bye for now.